Good afternoon and welcome to today's webinar on beneficial coal ash reuse, surveying industry opportunities. My name is Catherine Klein and I'm a technical advisor at NARUC's Center for Partnership and Innovation, where I support the Coal Modernization and Carbon Management Partnership between the U.S. Department of Energy and NARUC. Before we get started, I'd like to introduce today's moderator, Chair Mary Throne of the Wyoming Public Service Commission. Chair Throne has served as chair of the NARUC Clean Coal and Carbon Management Subcommittees, among many other activities. She's a busy lady. Prior to joining the commission, Chair Throne represented the Wyoming Department of Environmental Quality, Air Quality Division in the Office of the Attorney General. In her private practice, she's assisted in a variety of energy, mineral, and business clients with environmental compliance and permitting, industrial siting, and other regulatory issues. For 10 years, Commissioner Throne represented Cheyenne's House District 11 in the Wyoming House of Representatives, serving as minority floor leader for 4 years. Working in a bipartisan fashion, she played a key role in developing Wyoming's landmark carbon capture and sequestration laws. We are so happy to have Commissioner Throne and our panelists here today. Thank you so much. And with that, I will pass it over to you, Chair Throne.
Thank you, Catherine, and thank you for the kind introduction. I want to thank everyone for joining the NARUC Subcommittee on Clean Coal and Carbon Management for today's webinar on the beneficial coal ash reuse. Please note that today's webinar is part one of a two-part series. We invite you to join NARUC next month on February 15th from 2 to 3 p.m. Eastern Time for part 2 of this beneficial coal ash reuse series. That webinar will focus on exploring coal ash reuse impacts and barriers to entry. And Catherine will drop the registration link for part 2 in the chat for those who might be interested. Today's webinar is possible due to support from the U.S. Department of Energy, NARUC Coal Modernization and Carbon Management Partnership. We thank the DOE Office of Fossil Energy and Carbon Management for supporting NARUC's technical assistance activities for state regulators on coal and carbon management topics. Today, we're excited for our panel, and our webinar features Danny Gray, Executive Vice President of Strategy and Business Development at Echo Material Technologies, Bill Goodloe, Director of Technical Services at CEMEX, and Bill Easter, CEO at Semplastics. The webinar is being recorded, and the slides and the recording will be posted on NARUC's website and emailed to attendees next week. Please enter any questions you might have in the Q&A box, and we will get through as many as possible following the presentations. And now I'd like to officially introduce today's panelists. Danny Gray, as I said, is the Executive Vice President of Strategy and Business Development at Echo Material Technologies, a company dedicated to applying advanced technologies to manufacture low-carbon emission cements using natural and man-made pozzolans. And I neglected to ask how to pronounce that word, so if I got that wrong, I apologize. Gray was appointed by Secretary Muniz to serve on the DOE Federal Advisory Committee, National Coal Council. Gray served as chairman from April 2019 to 2020. He also served as chairman of associate members of the Southern States Energy Board in 2021 and 2022. Mr. Gray holds U.S. patent 9,873,638 for synthetic gypsum fertilizer product and method of making. Bill Goodloe is the U.S. Director of Technical Services for CEMEX Cement. That is kind of hard to say. He is a graduate of Auburn University in geology and has over 35 years experience in aggregates, concrete, and cement. He has been with CEMEX for 26 years, and his responsibilities include product quality, customer support, and product development. Bill Easter is a serial entrepreneur who is currently the CEO of Semplastics, XMAT, XBAT, and CBAT. Bill has been involved with materials R&D since his time at Bell Labs. As a measure of his innovation expertise, Bill Easter is currently listed as an inventor on 65 issued U.S. patents. So we have a very qualified and expert panel, and I will turn it over to Danny to get us started.
Thank you, Mary. If you could pull up the first slide. Yeah, as she noted, I'm part of Echo Materials, primarily focused on the green cement side of it. We are a company that specializes in beneficial use of coal combustion products, and I maintain that it is the most successful story under the Resource Conservation and Recovery Act that there is. Next slide. What I'd like to do is talk a little bit about the regulatory backdrop for CCR regulation and beneficial use. And I'm only going to touch on the highlights because we could spend days talking about the regulatory history. But basically, when the failure of the TVA pond occurred back in 2008, that set in motion some regulatory efforts at EPA to regulate coal combustion residuals. The regulations were passed in 2015 with an effective date in October of 2015. And basically they were under the subtitle D section of RCRA, which is the non-hazardous side of it. And that's where the fly ash, bottom ash, and gypsum requirements were nested. These regulations, when they were passed, basically set up a national criteria for managing the products, either in landfills or impoundments. Fly ash and bottom ash were commonly either slurried into impoundments where it was allowed to settle and decant, or either it was placed in the landfills in the latter years. Under the RCRA subtitle D CCR regulations, it had beneficial use was exempted because that portion of the recycling industry was very successful, had been very successful for many, many years, and basically needed to be encouraged. Within the CCR regulations, we introduced new terminology that introduced the encapsulated premise, and there was a definitional difference between encapsulated and non-encapsulated beneficial uses. Non-encapsulated beneficial uses were still allowed under a very strict set of criteria. Basically, I refer to them as the no harm criteria, but beneficial use in encapsulated applications was deemed to be preferred and acceptable. And that included things like use as a replacement for cement and concrete. Under the CCR rules, it was citizen enforcement, which obviously led to the potential for lawsuits. Congress stepped in and passed the WIN Act, which basically established the state primacy for the authorization and for enforcement of the rules. Under that program, the EPA was to publish guidance for states to be self-delegated under the CCR program, so that they would be the enforcement agency at the state level. Unfortunately, only a limited number of states have gone through that process, and today we only have a limited number of states. However, Subtitle D was a program that was intended to be enforced by the state agencies, and the state programs that were submitted for delegation, full delegation for enforcement, basically had to meet the standard that they would be at least as restrictive and protective as the federal rules. Otherwise, if a state was not approved and authorized, then the EPA was authorized to carry out enforcement. So as you see in the right-hand side of it, the resource value of the coal combustion byproducts is obviously important to our industry because it's used as a replacement for cement and concrete. It's been done for many, many years. And it's a win-win situation, but you can see that the volumes are dropping, which has brought about a change in the technology that's being applied to bring on more materials. Next slide, please. Basically, under the rules in terms of what is coal ash and how does it function within the in the recycling industry or within the mineral resource field, Basically, I refer to coal ash as basically 50 million year old dirt that happened to be with the organic matter that was settled out in 50 million years ago when the coal bogs were being formed. That mineral, which is the natural erosion soils of the time, that mineral ended up being nested in with the coal. And when you burn the coal, the mineral component does not combust, and it turns into either fly ash or bottom ash. But basically, the organic material is fired in the boilers, and it leaves the mineral component. So that mineral component is where we see the value, because it has pozzolanic properties, which means that it will set it'll add strength to concrete. It's important because it's already ground into a fine particle size, and it has the right constituents in order to be a pozzolanic activity within the concrete matrix. So it has tremendous value because of it. It's a powder, as you can see in the photograph to the right. It is a face powder type consistency material, but the fact that it's that fine powder and dry and usable as a replacement for cement is where the value comes in. I would argue that the beneficial use of coal ash meets in the biggest way, or the most successful way, the original congressional intent when the Resource Conservation Recovery Act was passed. Because if many of you probably not old enough like I am to remember that, but RCRA came in because of the energy crisis back in the 70s, and it was passed to promote recycling and recovery of the value of the resources. And that beneficial use of coal ash is the glowing star when it comes to that, because it avoids having to import cement in many cases, because it is a replacement for cement. The United States historically has been about a 20% import market for cement, and we manufacture domestically about 80% of it. That ratio is changing, and I'll leave it up to Bill to discuss that later. But if you think about this material being a byproduct or a waste product of the energy process, the fact that we can capture it and reuse it, put it to use in order to improve the balance of budget for the United States and avoid more imports has been a primary success story for many people in the value chain. It's, as I said, its primary use is for replacement of cement and concrete. That is an encapsulated use, and I would argue that it's a win-win-win proposition, because it reduces CO2 reductions on a global basis. It allows for a resource recovery that in turn saves taxpayer money, because fly ash is used as a cement replacement on infrastructure projects, highways, bridges, etc. That results in lesser cost concrete, which is at the end is a taxpayer savings, and just as important, ratepayers for the utility electricity ends up getting the savings, because whatever revenues are generated back to the utility for the use of the fly ash, that helps reduce the ratepayer base for the cost of electricity in your home states. Pozzolan has been in use for centuries. It started with the Romans and the Greeks using natural pozzolan, which was volcanic ash, and that was what was used, and that's why you see structures that are still 500 years old that are still standing today. But in modern day cement, it's a success story using coal-fired power plant pozzolans, as well as natural pozzolans. It's a modern day case story because it is used in recent decades. For the last 50 or 60 years, it's been used as a replacement for cement in modern day concrete. Natural fly ash versus coal fly ash is really a function of the fire source. And if you kind of look at it in a simplistic way, natural pozzolan fly ash is volcanic ash, which basically had the earth of Mother Nature there to form it. Coal fly ash, the function is basically a function of burning of the coal, which is just a slightly different source of the fire. So next point, next slide. In order to give just a reference, a quick reference to why coal fly ash is, or how it's used in concrete. Basically, concrete is the second most used consumed substance in the world. behind water, basically approximately 14 billion cubic yards per year. In the United States, roughly 40% of the concrete used in the U.S. or either around the world is used for residential infrastructure projects, and industrial commercial construction is the other components of it. So it's a valued asset that is a resource that we have a lot of emphasis on for cover. Concrete obviously is a critical mineral for society on a global basis. And it's projected it's going to continue to grow the use of concrete. In the United States, we use 100 million plus tons per year of Portland cement. And fly ash typically has a replacement ratio of about 20%. If you think about concrete in the diagram there, you basically have for the major components, you got the cementitious component, which is either cement or one of those subsets that you see to the right. And within a cubic yard of concrete, you have sand, aggregate, water, and some admixtures. And typically the cementitious component of it is going to be 500, 600 pounds on average per cubic yard of concrete. And what happens is that you can take out about 100 pounds of the cement and replace it with 100 pounds of fly ash. In general, that's just a quick summary of it. Next slide. So the trends that are impacting today is that, as we all know, the number of coal-fired power plants in the United States is reducing. Cement on a worldwide basis is under intense pressure to reduce the CO2 footprint of manufacturing Portland cement. In general, a little less than 1 ton of CO2 is generated for each ton of cement that's manufactured. It's a process that requires heat. It's a process that has some internal release of CO2. So if you look at it on a worldwide basis, USGS estimated that 4.1 billion tons of cement are produced. That's metric tons. And we're going to have 5 billion tons produced by the end of this decade. And you can see from a country origin of where the production is coming. China obviously dominates the cement production on a worldwide basis, and you can see in that graphic form. Fly ash substitution fly ash is in most concrete and is used to reduce the CO2 footprint of the embedded concrete. In the U.S., we have roughly about a 16% replacement of fly ash today. The cement industry is also working on advanced technologies to improve or reduce the CO2 or the clinker ratio in cement by using lime. And where I would like to talk about some examples is that on the new technology side, the industry is changing both from a CO2 perspective as well as materials that are being used in the cementitious side of it. We have manufactured SCMs or supplementary cementitious materials that include coal combustion products, but it also includes the natural pozzolan inputs. We have harvested fly ash and bottom ash coming out of landfills and impoundments in the U.S. now with beneficiation to apply. That's an important piece of where we're going down the road as fresh fly ash production continues to decrease. We estimate that there's about 2 billion tons. That's what our company views as the estimate of what's out there in either impoundments or landfills. That 2 billion tons will continue to serve as an input source for materials for us. Low carbon manufactured cements are on the cutting edge of new manufactured green cements that are low carbon. So we'll talk quickly about some of those. Next slide. Just some projects that we're working on where there's a project there in the upper right-hand side. It's basically we're mining a landfill in order to reuse the fly ash as a 20% replacement material. It offers an excellent environmental solution with without ratepayer negative impacts. It replaces expensive clean closure, and it meets the goals of reclamation and fulfills the market needs in that area. In the bottom right, we have harvesting cases where we're mining either bottom ash or ash out of impoundments and doing the same thing. Next slide. In the field of advanced green cement, you can see that in our company's case, we manufacture a low carbon footprint green cement that uses coal fly ash as an input and avoids the landfilling. We are actually able to manufacture a product that has a 50% replacement ratio. So instead of 100 pounds of cement coming out of that cubic yard, we would replace 50% or 300 pounds of cement in that cubic yard. And that is a way to help reduce the embodied CO2 in the material. There are advanced materials that you see pictured in the bottom photo for green cement. That's a 100% replacement for cement. And that what you see in that particular is a house that was printed with a 3D printer using this ultra low carbon cement out in the Austin, Texas area. So these are examples of where the market is moving and some of the trends that we see happening. Next slide. And that was it. I'll stop and turn it back over to Mary. Thanks.
Thank you so much, Danny. And we will just go straight into Mr. Goodlow's presentation.
Thank you very much. First of all, I want to apologize for my hoarse voice. I've developed a cold over the last day or two, but I think I can get through it. Go ahead. So I'm just going to do a brief overview of who my company is, who Cemex is, and kind of an overview of why coal ash products are important to us. But Cemex is a global building materials company that provides high quality products and reliable services with a rich history of improving the well-being of those it serves through innovative building solutions, efficiency advancements, and sustainability efforts. That is straight from our website. And our company was founded in Mexico, Hidalgo, Mexico in 1906. So we're approaching 120 years old. Next slide. And so Cemex has a worldwide presence. We operate on 4 continents. We are a cement producer and a ready-mix producer and an aggregates company. We've got 64 cement companies, 1,348 ready-mix plants, 246 quarries and distribution terminals, 269 and 68 marine terminals. So we have a presence all over the world. Next slide. In Cemex, our company is headquartered in Houston, Texas. We have 10 cement plants around the U.S., and we have 46 cement distribution terminals, 44 quarries, and 280, a little bit more than that now, 280 ready-mix concrete plants around the country. Next slide. So I just want to talk about why coal ash is important to Cemex and the concrete and cement company in general. Next slide. So how do we use coal ash and Cemex? Well, and some of this will be repeat some of the things that Danny mentioned, but it is a cement substitute in concrete. We try to use it in as much concrete as we can. And it also might be used as a raw material for our cement plants and as a finished product for producing blended cements. Next slide. So in concrete, and as Danny explained, from a coal plant, you get the fly ash that comes out the exhaust gases from the combustion process, and the bottom ash would come out the bottom. But fly ash is composed of silica and aluminum along with some calcium. And as he mentioned, it's a pozzolan, which means that on its own, it might not be that reactive, but the silica and alumina from it will react with the byproduct of calcium hydroxide from cement that'll produce more cementitious material. And fly ash might be classified as one of 2 different types, Class F ash, which has very low calcium, or Class C, which is a little bit higher calcium content. And whether it's one or the other depends on the source of the coal being used or burned. Next slide. So in concrete, there is a standard for fly ash that's used in concrete. It's C618, ASTM C618, which is standard specification for coal fly ash and raw or calcined natural pozzolan for use in concrete. And when it's available and when we can use ash in concrete, typically we use it at 20 to 30% replacement for the cement and the concrete. And some applications, it might be much higher, as much as 50% or more for certain applications. Next slide. So for concrete, for Cemex, as I said, we have 280 concrete plants around the US. And fly ash is vitally important for us. We use it wherever possible. The whole industry, concrete industry, wants to use it whenever possible. It's not always available in certain areas if there's, not power plants close by. So it's a market specific thing. But it also enhances properties in concrete. I think early on fly ash was probably used more for economical reasons, the price of it compared to cement. But we've learned that it has very valuable properties to enhance concrete, such as sulfate resistance, which helps it when concrete gets placed in soils that are high in sulfates, which can attack the concrete. It's resistant to that. It's helped resist alkali silica reactivity. And what's really become more and more important now is the fact that when we replace cement with fly ash, we're reducing the CO2 per yard of concrete. And I know some of you are familiar with what EPDs are, environmental product declarations. We're developing those now for our concretes where we determine the global warming potential in concrete. It's kind of like a food label where you show the ingredients and the calories and such. We're determining, on each concrete mix design, what the global warming potential is for that in terms of how much CO2 it has. And I know you can't read that little graphic, but basically, the more ash you're able to use in the concrete, you're going to lower the CO2 per yard of concrete, which is very important to us in the industry today. Next slide. We also, in some cases, use fly ash as a raw material because to produce cement, you need materials that contain calcium, alumina, silica, and iron. And, fly ash could potentially be a good source for some of that. Whatever the source of materials we're using, we grind these up, we proportion them, and we feed them into the cement kiln at temperatures up to 2,600 degrees, and we basically cook it. And what comes out of the kiln is called, clinker. We take that, and it goes to a finish mill along with some gypsum to control the set, and we grind it, we come up with cement. But in some cases where the material's available and it's the right chemistry, we can use it as the source material in our cement plants. And we have a number of plants that are currently using sources of coal ash, be it either the fly ash or the bottom ash for those plants. So it's very important to our industry there. Next slide. Now, another use for these products that we are starting to see more and more of is blended cements. Cements historically are just Portland cements, which were just clinker from the kiln, gypsum, and you grind them in a finish mill. As Danny mentioned, we're starting to add limestone in it to produce Portland limestone cements. But there's also some other blended cement options that are allowed in C595 standard specification for blended cements. We can take basically cement and fly ash and blend it, grind it in our finish mill, and produce a finished product that contains both the clinker or the cement and the pozzolan. And that would be classified as a type 1P cement. So that's clinker, the coal ash, and the gypsum. There's also a 1T product, which is a ternary or 3-product type of cement, which might have clinker, coal ash, gypsum, and additional products such as limestone or slag. And so these blended products are becoming more and more important for the cement industry because it helps lower our CO2, which, is very important. There's a lot of pressure on the cement industry to do so, and we're working very hard in these blended products to help do that and to lower our CO2. Next slide. And so that's kind of the basic uses for Cemex and the concrete industry in general. And for Cemex, where do we get these products? Well, as we mentioned, the fly ash comes from power plants. If we're using the raw material, which, you know, may be the bottom ash, they also come from the power plants. And for blended cements, it could be those same sources. But what we're also doing, and what Danny mentioned, is the use of recovered ash from waste ponds, which that's going to be a very important source of material for our industry. As he mentioned, you know, there's less and less coal burning power plants. The available material from that is getting less and less. And so it's going to be important for our industry to be able to utilize the ash. And there's millions and millions of tons of ash in the ground. And so at Cemex, we are looking at and have made trials of producing blended cement products with some of this recovered coal ash. Next, please. And I think that's it. Just a quick overview.
Thank you, Bill. Now we'll move on to Bill Easter from Simplastics.
Thank you, Chairman Throne. Great hearing about how coal ash, fly ash has been used, and I learned a lot. It's quite amazing, quite successful as it's being used. So we're going to transition a little bit, look at a little R&D now. Next slide, please. So we're a small company. We're in Florida. We do a lot of R&D. We've received over $14 million in research grants and contracts from the Department of Energy, Space Florida, NASA, and we work on specialty high performance material systems. Next slide, please. So our values, vision, and mission. Our values: serve our customer, love our people, respect our vendor, enjoy the journey. The vision is reimagining high-performance materials, and our mission is empowering each customer to achieve market dominance by creating customized, sustainable materials. And we're going to focus on this idea of sustainability. It's thrown around a lot. What can make it successful in the marketplace? Next slide, please. So we like to talk about kainos, Greek word for taking something that's been devalued and making it, renewing it, recreating it, carbon framework. And so we repurpose both undervalued and waste carbon feedstocks to create valuable, customized, sustainable products. And people talk a lot about sustainability, and they primarily mean environmentally sustainable. But as we know, if it's not economically sustainable, those subsidies go away, and then the benefit of that environmental actions can sometimes go away too. So for sustainability, it has to be both economically sustainable and environmentally sustainable. So how do you do that? Next slide, please. So as you know, we're an R&D company doing a lot of different things. So on the left side of the figure, you see feedstocks, and there's different things that are either undervalued or they're waste. Produced waters, geologic waters, wastewaters, those come from oil and gas, spent graphite from lithium-ion batteries, CO2 gas, which we'll just touch a little bit because we're excited about that, coal and coal ash. So we're going to talk about CO2 gas, coal ash specifically with engineered aggregates, carbon negative building materials, coal derived building materials, high temperature 3D printed filaments, and high performance plastic fillers. And we're going to really highlight high performance plastic fillers as something that we were successful to use with the coal ash. Next slide, please. So what kind of high value products can you make from coal ash? So we've completed a Department of Energy contract, $1 million federal share, $400,000 cost share. And we're using a technology called polymer derived ceramics. That's something we use inorganic polymers for everything that we do. And in this, the sort of plastic turns into a ceramic in a very cost-effective way, much more cost-effective than typical ceramics in terms of energy usage. So we put a polymer-derived ceramic coating, and we also significantly reduce the leaching of undesired elements. You can see on the right pictures of these columns that we made. The compression strength's about 6,500 psi, and they're made of 60 to 80% coal ash. Next slide, please. This is taking the coal ash and putting it into plastic, and so we picked polypropylene. It's one of the two most known plastics or used plastics, and so amazingly, so if you typically buy polypropylene, you can get 30% mineral filling of it. We were able to put up 70% by weight. So you can imagine using a recycled polypro, which again is incredibly inexpensive, with fly ash, and being able to turn that into products. So the PDC coated coal ash can improve the properties of the plastic it is loaded into. Actually, the stiffness doubled, and if you see on the left, the bar graph, the temperature of normal polypropylene is 201 F that we tested, and then you got almost an extra 100 degrees Fahrenheit in terms of heat distortion testing, and that's quite significant because 212 is boiling water. So what this says is this thing can survive that. And it has it's the same matrix. It's using polypropylene, but we're filling with 70% fly ash. So you can also see on the right, you can see the pellets. Oh, excuse me. Just go back just a little bit. Okay. For the pellets, now I must have it. The pellets on the right are what you turn into the plastic, and you can see on the right corner 3D printing. So we're able to 3D print this as well, which is pretty cool. Next slide, please. So future work, what we're looking at, cooling tower plastics, protection barriers. Anyone in the audience has something else that they think we can do with plastics, we're happy to look at that. We're being written into, there's a power plant in Virginia, West Virginia, that they're studying. They have millions and millions of tons of fly ash, and they're looking to decommission this plant, and they're looking to work with us for what we might be able to do with that ash. Next slide, please. So just want to talk real quickly about, we're also taking CO2, we're bubbling through wastewater, and we're able to make mixed carbonates. We dry them. Again, we use that same resin. We're able to cure it into panels, which is pretty amazing. So that panel on the right has 30% sequestered CO2 in it. Sort of hard to believe. Next slide, please. And again, just talking about it, is that we're able to take any CO2 source, could be direct air capture, point source. Even the prototype you saw, we hooked up the gas from our carbon dioxide from a pickup truck. And the CO2 is permanently captured. It's almost like a synthetic limestone kind of process. And we're not really concerned using it as an aggregate, the purity of it. It can have calcium, magnesium, strontium. It doesn't matter. And so this methodology allows you to take brines and those kinds of things and turn them into products. And then you can take the water and clean it up and either use it for agriculture, or if you do really good, you can make it potable. Next slide, please. So the ask is, we've done this research, we have some great results. We're seeking partners to help move the technology from lab scale R&D towards implementation and commercial at a larger scale. Next slide, please. There's points of contact. There's our information if you have interest in this. And thank you so much for the opportunity to present our work.
Well, thank you, Danny, Bill, and Bill. That was just fascinating information. We have a couple of questions from the audience, so I think I'll go to those first. A pretty general question. How much fly ash is being taken out of landfills today? And similar question for bottom ash.
Sure, I can take a stab at it. I think it's the American Coal Ash Association does that type of survey in terms of the beneficial use of coal combustion byproducts for various applications. They don't report how much is removed from landfills right now. However, that is in the change for the future years that they will publish that. I will only give what my estimate is, or our estimate is. We estimate that there's probably less than 4 million tons of fly ash and bottom ash that comes out of landfills today that's going into a beneficial use. However, we know just from our own use that that number is going to increase substantially between now and the end of this decade. As an example, in 2022, the latest publishing year, according to ACAA, there was about 11 million tons of fly ash that was used in cementitious applications. We know that that number, as we close down more and more power plants, and that number is not going to shrink because of demand. It's going to shrink. Fresh fly ash is going to shrink on that side by fresh production. However, we estimate that by the end of this decade that the demand for fly ash will be transitioned to recovered and reclaimed harvested materials, and the volume is going to be double what was used in 2022. So we're estimating that 20 million tons will come from various landfills and or ash impoundments between now and the end of this decade. So that's our estimate of it. The data is not published as current, but I do know that they are working on trying to include that type of information from users out in the market. And Bill, you may comment from cement side, because when I look at it as a fly ash substitution for cement, which is the pozzolanic type ASTM C618 material. But there is a lot of both bottom ash and fly ash is used as a raw feed input to the cement manufacturing process. So
the percentage of what we use at this time from recovered ash is pretty small. But like you said, I think that's only going to get larger and larger as we go.
Okay, thank you. Should I be embarrassed that I didn't know how to say pozzolanic? But anyway, never mind. Now I know. We have a couple more questions in the chat. So are there any negative externalities like increased VOC off-gassing during curing, or any depreciated structural integrity of the finished concrete product that's been exhibited by substituting or blending fly ash and cement in concrete?
I'll take a stab at it first, and then I'll turn it over to Bill, because I've seen this question pop up before, but to our knowledge, there is no VOC increased gassing related to use of fly ash in concrete. As a matter of fact, quite the opposite was what you would expect from physics, simply because fly ash, when you add it to concrete, it actually decreases the what I call the transmissivity or the permeability of the concrete, because it helps fill in the gaps of the aggregate much more efficient. So I would expect there is a decrease in that. From a structural integrity standpoint, fly ash actually improves the long-term life cycle of concrete because of what it brings to the chemistry and how it reacts in order to make the cement more efficient on a long-term basis. So, there's no structural degradation. And I think that bears out witness from what you see in Greece and Rome, because the ancient structures that we see today, which have fly ash in them, the only reason those structures have survived is because they did have pozzolanic materials in them when the Romans and the Greeks installed it. So, and I'll turn it over to Bill with that. So.
No, Danny, I would completely agree with everything you said. I think fly ash only enhances the property of the concrete. The fly ash, being a flue gas, is very spherical. If you looked at it under a microscope, it reduces the water demand in the concrete, so it's a denser mix. It's got better durability, so it's going to hold up in the ground for foundations and piers and that sort of thing. And so I'm not aware of any of the issue related to the use of it. It only makes a better product.
Thanks. And now I'm going to bring Bill Easter into the conversation because I think this one is for him. What can the sequestered CO2 panels be used for? Does the CO2 stay suspended in the panels indefinitely?
Great questions. I think it can be used as aggregates. It can be used as it's a beautiful part. I always like to show people parts. It can almost look like a countertop or a backsplash. It can be used in a lot of different things. Why it stays in there is it is limestone. When we use a thermographic analysis, it handles to 600 C. So 100 C is boiling water. So it'd have to be quite a fire, and then you might want the CO2 if the fire hits, to put it out. So it might have some firefighting at those temperatures, but it is permanently sequestered. So it's quite something.
No, and in our Clean Coal Carbon Management Committee, we want to. This is just a great conversation because we want to shift more towards utilization, the utilization discussion. So this is just giving me all sorts of ideas. I think our last question in the Q&A is, what type of processing is required to reclaim the landfilled fly ash?
A good question. And the answer is not easy, but I will say it varies depending upon how the ash was placed in the landfill, whether it was commingled with bottom ash or kept separate. The photograph of the site that we were reclaiming the landfill is a monofill, meaning that is only fly ash was placed in that landfill years ago. And then it drops down to another level of technical perspective is if the fly ash and bottom ash were combined, then obviously you either have to separate the two products because one is granular, the bottom ash is granular, and fly ash is smaller particle size. Ultimately, you want everything to be the same size, particle size as the fly ash is in the matrix. So the materials coming out of the landfill need to be dried. They need to be milled if they have bottom ash mixed in with them. If we're like our project that's using milling bottom ash, we basically mill the bottom ash in order to get to the same particle size range as fly ash. So there's the level of technology and mechanical treatment and or drying is dependent on every situation. So in some of the ash impoundments, you may be removing ash out of an impoundment that is saturated with moisture, so it obviously requires more drying and processing. And if it has other constituents in it, they have to be separated. It's not unusual to see a hard hat once in a while in a landfill, or a welding rod or something like that. So obviously we have to have mechanical systems for separating all of that type of pieces of various debris and things like that. So.
I was about to ask, what is the strangest thing you've ever seen in a landfill? But maybe don't answer that question. Oh, looks like, we're getting into the regulatory side again. Has EPA performed a risk evaluation or risk assessment of fly ash use in concrete? Or is that covered in the RCRA?
Yeah, I think they have. I think, obviously EPA's performed multiple risk assessments related to fly ash use in various applications. In particular, early on, they did do the risk assessment for use in concrete. If you think about it, use of fly ash in concrete is one of the easier applications in terms of embedding it or encapsulating it in concrete. Even if you were trying to dispose of a product, quite often mixing it with cement into a concrete matrix is the way you would want to manage it. So from a practical standpoint, it makes sense. The risk, EPA has done the risk assessment on it.
Yeah, putting it in concrete it's really a win-win because it ultimately makes a better concrete product, and then you take it out of the environment and you capture it in concrete.
So I think this next question ties into our utility world. It's basically, I agree that the beneficial reuse of coal ash and concrete is a great recycling story. Specific to ponded ash, the challenge utilities are facing is the cost to excavate, dry process, sometimes treat for carbon, and then transport and sell to the market. So who bears the costs for such a great recycling story, or is there and I'm adding to the question, or is there profit to be made for the utilities? And what should we regulators do to kind of nudge this along? Bill, you look like you
I'll
were
jump
ready to
in.
jump in.
I'm the crazy guy here, but mineral fillers are used. They're in the hundreds of billions of pounds, and you know what they go for? 20 cents, 30 cents a pound. So can it be? I don't know. I put my stuff. That's a possibility. So you have to move the value up if you're gonna. It has to pay for itself one way or another. And that's the problem. If no one's going to pay for it, then it sits there, right? And can we find a use where it's economically viable? And, that's the question.
Danny or Bill Goodlow?
Sure. I'll take a stab at it. The beneficial use of coal combustion products is proven to be a win-win for the utilities, and as well as a win-win for ratepayers, as I said earlier, taxpayers who are basically getting the value of the cementitious material in road construction and the value that it brings, because fly ash typically sells for less than Portland cement. So naturally, there's a savings to the concrete, and that savings on the concrete ends up vesting with the end product, which is the road or the highway or the bridge that's being built in order to use that concrete. So highway departments across the nation rely upon fly ash to help them hold down construction costs in their infrastructure. So that, from that perspective, is there profit in it? Yeah, I mean, obviously people do it for a business purpose. And the good thing about this industry is that it is a three-way win. From the environment is improved, you're taking materials and recovering it out of landfills or impoundments, you're reducing the CO2 footprint on a global basis, and it's paying off for the taxpayer and the utility ratepayer. So I still maintain it's one of the most successful RCRA stories that you could possibly ask for.
And, speaking as a regulator, I know one of our coal-fired plants in Wyoming, the cost of complying with the CCR requirements is one of the reasons they're looking at closing it. Their air quality reasons as well. But is that something you think we should ask from a regulatory standpoint? ask companies to evaluate rather than just sort of punting and saying that they can't afford to meet the environmental regulations, so they want to close the facility.
Well, it's
I'm
a
speaking hypothetically here.
yeah, yeah. Hypothetically, I mean, it's a complicated scenario. As we know, we as the industry and the energy business transitions to renewables with a larger portion of that, power plants, whether it's coal or gas or whatever, we still have to maintain system reliability and stability. And those plants serve a purpose and a role in that arena. So that drives a lot of the analysis because your power system needs stability and reliability. The other component, simply from an environmental standpoint, what I would say to utility regulators is that, number one, the beneficial use is the most appropriate way you could use any material that's on the site or what is produced at the site. So to the extent that from a regulatory standpoint, you can encourage that, I would advise that would make economic sense for all parties. Number two, it works for the environment. And it saves, on compliance cost, it saves on closure cost, it saves on ultimate liability that will descend to the ratepayers in that area. So I would say to the extent that you can encourage it, I would.
Okay, well, thank you. We're getting close to the end, but I wanted to mention and see if he wants to say anything, that Tom Adams, who's the executive director of the American Coal Ash Association, is with us. I think he had his hand raised. I don't know if we can let him in, or I'm looking to my facilitators.
Sorry, it looks like he might have dropped off the call. I'm not seeing. Oh, here, maybe it's. Give me one more second. Okay. Yes. Okay. Here we are. Hi, Thomas.
Hi, good afternoon. I see the point I wanted to make was answered already in the chat box, but EPA as recently as 2015 did an evaluation, of the safety of using fly ash and concrete and FGD gypsum and wallboard, and they found that there is really no impact, negative impact from using fly ash and concrete or FGD material in wallboard. So they went ahead and did that, and they used a risk evaluation protocol that they had developed to support their regulatory efforts. So that was the most recent effort they've taken on that subject.
Well, thank you, Mr. Adams, and thank you for joining us. I thought we lost Bill Easter there for a moment too, but
we did. I'm back. I moved.
Well, I think we're out of time. But if there was something you wanted to say before at the time you disappeared, feel free to jump in.
We're happy. We're neophytes. We're at the beginning. Danny and Bill have very established, very successful businesses. So if there's interest in looking at potential applications, specifically plastic fillers, to me it makes a lot of sense. Just give us a shout out, and let's see if we can find a market to pull this through, right? Because you have to have markets. There has to be a place for it to go, or it's just a science experiment.
Right, and yes, we like to move from the lab to commercially available. With that, I want to thank our panel. This was a great way to spend an hour from my perspective. Thank you, Danny, Bill Goodloe, and Bill Easter. Want to remind everybody that the registration for NARUC's Winter Policy Summit in Washington, D.C. From February 25th to 28th is open, and you can find that information on the NARUC website. And again, at that event, the subcommittee on clean coal and carbon management will have a panel on Sunday the 25th. And our topic is the economics of carbon capture, getting it done. And again, we'll share the presentations from this webinar via email with all attendees. And the recording will be on NARUC's YouTube channel. Thank you again. I almost forgot the DOE Office of Fossil Energy and Carbon Management for supporting today's webinar. And if you're interested in anything else NARUC related, I encourage you to go to our website. And thanks again to the panel, and thanks to staff for getting us organized and keeping us going. And thanks to all the attendees. We really appreciate it.
Thanks. Have a good day.
Thank you.
Thank you very
Bye,
much.
everybody.
Bye.
Bye.